In this video, we'll discuss data abstraction and pairs. So recall that abstraction is a technique used by languages for coping with complexity. So we've already seen examples such as procedural abstraction, where we created compound operations and then provided a very simple interface, just the function name and its parameters. And this separated the implementation of those procedures from the usage of those procedures. So complex operations could become very simple units of expression, which enhance the expressive power of our programs. And then we saw with higher order functions, we could enhance that expressive power even further by having functions that operate on other functions as data. In this chapter, we'll discuss data abstraction, which is pretty much the same thing, but with data. There's two key aspects to data abstraction. The first being we need to structure some data together, so we're going to combine simple pieces of information like numbers, etc., to form compound pieces of data, which can in turn be treated as singular units of data in our code. This increases the expressive power. For example, lets us say things like, this is a list of all the even numbers from 1 to 200. And we can conceptually hold that as a singular entity in our code, rather than having to refer to all 100 numbers individually. And the second key aspect of data abstraction is that it provides an interface. So it separates how that data is used from how it's constructed. So the interface is a set of procedures where we have constructors for joining data and selectors to access separate parts of that data. Now, if we have data abstraction in our programs, it's going to elevate the conceptual level of our program. It's going to bring it closer to the domain level or the human level, which will simplify readability and also increase modularity of our codes, which makes it easier to design, debug, and maintain, as we will see. For the construction of complex entities out of simple ones, Scheme provides a glue known as pairs. So a pair is a structure that has two fields, and it's implemented by an interface of three procedures. The first procedure is known as cons, which is a procedure that takes two arguments and constructs a pair object out of those two arguments. Char is a procedure that returns the first element of a pair, and CDR is a procedure that returns the second element of a pair. Now the names char and CDR they're a bit odd, but they come out of historical reasons. Char stands for the contents of the addressable part of the register, and CDR stands for the contents of the decrement part of the register. Which is to say, back when Lisp was invented on the IBM 704, both the char and CDR, that's a pair, was stored as a single register, where the char and CDR were the two halves of that register. So two pieces stored in one memory location on the machine. And then cons you can think of just stands for the word construct because it creates pairs. Another useful procedure when dealing with pairs is the predicate function pair question mark, which determines whether or not the argument it's looking at is in fact a pair. So let's take a look at some examples. So if we want to create a pair object, we can just say cons, for example, 1 and 2, two values, and it joins them together into what's known as a dotted pair. So a dotted pair is just the long term for a scheme pair, where we have the first element 1, some symbolic description, the dot saying that these two things are separate but joined, and then a 2. So this does not say 1.2, it's not a single number, it's 1.2 to say these two things are held together in the same conceptual object. So the dot is just for display and can be safely ignored. We can also bind these pair objects, these things that cons returns, into a variable. So I can say, for example, define x to be cons 1, 2, and I can ask what is the value of x, and x is just the pair 1.2. I can similarly define y as cons 3, 4, and ask what's the value of y, and it's just 3.4. I can ask, are these things pairs? So pair question mark x, and that's true. Similarly, pair question mark y should also be true. It's just a different pair. Now, that's the constructor that brings items together into a more complex item, but we may still need those individual items further on down the road. So if we want to access the different parts of a pair, we can use char of x, where x is the pair 1.2, and this returns the first element in that pair. And we can ask CDR of x, and that will return the second element from that pair. Now pairs are orthogonal in that the thing that comes out of the cons operation can also be the argument to the cons operation. So I can, for example, say cons xy and say, call this z. And now z looks like this, 1.2, 3.4. Now the pretty printing here ends up looking a bit odd. In this case, we would expect it to look more like 1.2.3.4. And indeed, that is what's happening in the background of Scheme. The reason it looks a bit strange here is, in fact, just because of pretty printing. The middle dot here and the last set of parentheses are removed. The reason for this will be a bit clearer later on. Essentially, pairs are used to create more complex structures like trees and lists. And since lists are so prevalent in the list processing language, the pretty printing is designed assuming that you have a proper list. So we'll discuss that later on, but the idea here is the pretty printing for pairs doesn't always look exactly what you'd expect it to do, but the actual structure is the same. So I can say the CDR of Z, for example, and that is that other pair. I can ask the CDR of the CDR of Z, and that should be the last element of that last pair. Okay. Now, in order to visualize pairs, we have what's known as the box and pointer notation, or box and pointer diagrams. And it's a simple linked list type diagram where each pair is represented by two conjoined boxes here, and nested pairs are represented by references to additional pair objects. So for example, the symbol cons 1, 2 would create a structure like this, where if we defined it as x, for example, there'd be an x off in the corner here pointing at this pair. The pair has two boxes, where the first box points at 1 and the second box points at 2. The direction of the arrows is essentially irrelevant, although by convention typically the car points down and the CDR points to the right. The reason for that again is because lists, but we'll talk about that later on. But let's just walk through some of these. So cons 1, 2 creates a pair like this, but if we have a pair of pairs, like the value we called Z in the previous example, we say cons 1, 2, cons 3 and 4, and then cons those together, we get a structure like this, where we have the first value, which we called x, was cons 1 and 2. Over here we have cons 3 and 4 as the second value, which we called y, and then we cons those two things together. So the car of Z gives us what we called x, and the car of Z, or sorry, the CDR of Z gives us what we called y here. Right? And we can combine these things in all sorts of different ways. So for example, if we said cons 1 to cons 2, 3, and 4, it gets pretty quickly confusing, but with some nice formatting, we can see that the outside cons here is consing some structure to the value 4, and we see that exactly here. The first pointer goes to some structure, and the second pointer goes to 4. Within that sum structure, the car of this overall data structure, we could say cons 1 to cons 2, 3. So cons the value 1 to some pair, and that pair has the values 2 and 3. So with all of these, we can walk through and say, well, if I wanted the car of this block, let's say, the car would be a 1. Similar, if I wanted the car of this block, we could just follow this pointer and say, well, the car is 1, 2. If I took this expression, said the car, well, it would return this first element, which we can see is the block 1, 2, 3. All right, let's do a little bit more practice here. So let's return to Dr. Racket, and I'll create an example here. So define ex1 is what happens when we say cons 1 to cons 2, cons 3, 4, and then a 5. So probably hard to visualize what this pair structure ends up looking like. So let's start by manually visualizing it. Let's create the box and pointer notation for this specific example. So let's get the whiteboard up, and if I can't get these both on the same screen. Right, so the box pointer notation starts with, we're defining the result as ex1, so let's say ex1, and then we'll create a line from that. I don't have arrows here, so lines represent pointers, and that's a pointer to a pair. Okay, so a pair looks something like this, where we have a box with two fields or two elements to it. Now in this case, we're saying the ex1 is going to be the result of this first cons here. And this first cons says cons 1 to everything else, which means the car of this box points to the value 1, and the CDR of this box points to a new cons. So we create another box here, put a line through it. Now we have our second element here. Now this one says cons whatever this is, the cons 2, 3, 4, so cons all of this to the value 5. So the CDR on this one's a bit simple, so let's start there. Take that, and that becomes the value 5. But the car in this one is this whole combination, right? This cons this combination to the value 5. So the car here points to another box. Okay, so create that pair. Now the car of that pair, so we're now looking at this box. The car of that pair is a 2, and the CDR is another pair. So if we say the car here, point that at the value 2, and the CDR here points at another pair. In this case, box, the pair, the line down the middle. In this case, this pair is cons 3, 4, so 2 terminal elements. So we have 3 here and 4 there. And there's our box and pointer notation for this specific example. Now, with the box and pointer, it's very easy to see the answer to some simple queries. So for example, if I said, what is the car of EX1? Well, maybe you didn't need the box and pointer for this one, but you should be able to figure out what that is. So the car of EX1, if we go to the box and pointer, says we start here. This is EX1. This is the pair that it's representing. So the car of that is just the value 1. Okay. And we can run that to test, run our code, and we get the value 1. Okay. We could ask a slightly more complicated one. What is the CDR of EX1? Which again, maybe you could figure out from this because it is just a single step. But to take a look at the box and pointer, we are here, we take the CDR, and the CDR is this whole block here. So that's 2.3.4.5. So it's this whole structure. So we should expect it to look something like the pair 2.3.4. That's all together. And then that whole thing is cons to the value 5. Now again, pretty printing will make it so that it doesn't look quite like that, but we get pretty much the same thing here. So 2.3.4 gives us something looking a bit like a list actually, but all the values that we expected are there, just they print a bit strange. Now to prove that they are all in fact there where we'd expect them, we can walk through this a little bit more. So we could say, for example, what is the car of the CDR of EX1? Right. So from this depiction, using dot notation, we can take a look at that this whole thing is the car of this, which was the CDR, right? If the CDR gives us this part, which is this whole expression here, the car of that is everything before the outermost dot. So it'd be that. Now from this drawing, it's not quite as clear, but it should be the same thing, 2.3.4. And from the box and pointer notation, we can say, we take the CDR, so if we're at EX1, right, we say the CDR of EX1, so we follow this line. And then the car of that says follow this line, so we should get 2.3.4. And if we run that, we get basically that answer, but again, the pretty printing changes how the dots and brackets line up. Okay, let's do one other example here. What happens if I ask, what is the car of EX1? So what is the value of this expression? So if we take a look at the box and pointer here, so this is EX1, this first pair, and if we take the car of that pair, we end up at 1. And if we ask, what is the car of the integer 1? Well, that doesn't really make sense, because the car is for removing the first element out of a pair, and an integer is not a pair. So this should give us an error, and if we run our code, this error here. mcar, contract violation, expected m pair given 1. An error you're very likely to see very often. This essentially means you're trying to open up or access elements from a pair when you aren't actually dealing with a pair. So you're applying car, typically speaking, to one of the elements of your pair rather than the pair itself. All right, let's do another one actually. So how about the car of the CDR of EX1? Again, notice the order of operations here is from the right to the left, essentially. We're starting from the innermost bracket here. CDR of EX1 says follow this line, which puts us at this combination. Then the car of that says follow this line, and then the car of that says follow this line to the value 2. So if you read this, make sure you're reading it in the correct order. So CDR of the first element, and then the car of that, and then the car of that. And the brackets tell you that. The bracket says take the car of the result of these other operations. So if we run all of this, we expect the value 2. Nope. And we're going to have to get rid of our error so we can run it. And there we go, we get a 2. All right, similar question, but maybe in the opposite order here. What would we have to type? So I'd say underscores. Well, that doesn't work. Fine. Hyphens, because they're visible. And I'll fill in those blanks in a second. What of those hyphens gives us the value 5? So the value 5 in our diagram is here. What would we have to type? It would be the what of the EX1, let's say. Possibly multiple steps. So try and figure this out. Pause the video if you must, and let's figure it out together now. So if we have EX1, that's this entire combination. If we want to get to that 5, we want to follow this line and then this line. These are both CDRs, so it actually doesn't matter which order we type them in. We could just say the CDR of EX1, and then from that we'll take the CDR again. So in this case, the first CDR, the highlighted one here, takes us into this block here. And then we say the CDR from there gives us the value 5. If we run our code, we get a 5. All right, worth mentioning that Lisp provides sort of convenience combinations or compositions for all these sort of multiple step operations like the CDR of the CDR or the car of the car of the CDR. Essentially up to 4 levels deep we can say things like, what's a good value? We'll use EX1 here. We can say the catter of EX1. Sorry, EX1. And this actually translates to the car of the CDR of EX1, which I think we already have is 2.3.4. So if we run this, we expect to get 2.3.4. If we run this, we can see the exact same answer. So catter here is a nice short form for doing that. Do I have another decent example here? I'll just use the existing one here. The car of the CDR is CAADR of EX1. So that matches this example here. We should expect to see the value 2 as our answer. And we do in fact get 2. So when you're dealing with these composition operators, they go in the same order. So the car of the CDR. So if you're resolving these, start with the last letter first. So that's saying the CDR of EX1, from that take the car, and from that take the car again. Just like we did here, just a lot simpler to type. So this one we would expect to be the value 2. I believe I already ran this. We get 2. All right. So let's take a look at data abstraction using pairs with a working example of rational numbers. So a rational number is any number that can be expressed as a fraction of 2 integers called the numerator and denominator respectively, where the denominator is non-zero. So we'd like to be able to construct this notion of rational numbers, ignoring for now that Scheme actually has rational numbers as a built-in type. We'll construct our own version of rational numbers that's able to perform arithmetic that we would normally do on rational numbers. Specifically, we can add 2 rational numbers, subtract, multiply, or divide them. And the equations for each of those are here, where n1 represents the numerator of r1, and say d1 represents the denominator of r1. So this equation for adding 2 rational numbers says take the first numerator, multiply it by the second denominator, take the second numerator, multiply it by the first denominator, add those 2 quantities together, and divide the whole thing by the product of the 2 denominators. So what we want to do is be able to create rational number objects that we can represent as a single entity in our code, but still have the ability to pull out the individual pieces so that we can do the rational number arithmetic when it comes to it. So rather than using pairs directly to store 2 values, we'll construct an abstraction around that. The reason for this is that data abstraction will make our code more robust and easier to read. So the interface that we'll construct will consist of a constructor and selectors, as well as the conditions that they need to uphold in order to be a valid representation. So the constructor creates the abstract data from the primitive data, so it creates, in this case, the rational number out of the integers. So it's essentially the glue that combines these 2 things. So given 2 integers, we'll make a rational number somehow. The selectors will then take a rational number as their argument and extract the primitive data out of them. So we get the numerator or the denominator out of the constructed rational number object. And then the representational conditions are the idea that we need to be able to make certain assumptions about this data that gets constructed. So for example, if x is the result of make rational of two values a and b, then the numerator of x divided by the denominator of x should be the same thing as a divided by b. So our representational condition here. So if x is the result of make rational ab, then the numerator of x and the denominator of that rational number object will be the same thing as if we had just divided the original two quantities a and b together. Okay? So that's the representational condition, the behavior that needs to be specified or needs to be maintained by this interface that we're constructing, make rational numerator and denominator. Notice we haven't said anything about implementing these behaviors yet, just the interface that we can use in order to construct the abstraction that we need. So the specific implementation, or at least the initial implementation that we'll use, will be storing rational number objects as pairs. So the constructor then is just consing two things together, right? Make rational can be cons a, b, essentially. And the selectors, if we want the first element or the second element, numerator could just be the car of whatever value we get, whatever rational value we get, and the denominator can just be the CDR of that rational number. So let's construct these in our code here. So we can say define make rat, short for make rational, for num and denom, short for numerator and denominator. And that's just going to be essentially an alias to cons num denom. And again, this may seem a bit pedantic. Why bother even using this other form instead of just cons? And the reason being, when we're talking about rational numbers, they could be represented as cons, but maybe they'll be represented as something else. And we'll come back to that notion in a second. Let's just finish constructing this abstraction barrier for now, though. So we got numerator. There's a function that takes in some rational number and returns the first value, which is the car of that rational number. And then we have define denominator of some rational number, and that just returns the second element of that combination, which is the CDR of that rational number. So essentially we are just aliasing these things, but we'll change them later on, and we'll see that aliasing, while useful here, is not the best system either. So let's make use of these things. First, let's try constructing a rational number. So I can say something along the lines of define the variable 1/3 to be make rational between the integers 1 and 3. And if we run that, oh, sorry, make rational doesn't exist. Call it make rat. There we go. Now that doesn't print anything out because it constructs that object, but we can ask what is the numerator and the denominator. So what is the numerator of 1/3? What is the denominator of 1/3? And if we run this, we get 1 and 3 as expected. So we construct this object, and then later on in our code we can access the individual elements of that object. But in this case, if we ask what is that object itself, typing in 1/3, we see it is just in fact a pair object. That's a bit of an issue because people using this code, this rational number construct that we're designing, wouldn't want to see the underlying implementation. We'd like to treat these rational numbers as rational numbers. We shouldn't be treating them as pairs. We should be treating them as rational numbers. And the underlying abstraction, these functions here that we created, should be the only thing that are aware of the underlying implementation details. Everything above these functions, such as using these functions, should all hide away the fact that they're pairs and support the notion that we're dealing with rational numbers, which is to say, our behavioral conditions should also include the display of rational numbers. So we'll create another function here to accomplish that. Call it define print rat, which will print some rational number. Call it x here. And this is just a pretty printing for rational numbers. So we'll say display the numerator of x, display the slash symbol, display the denominator of x, and then a new line just so that it ends nicely. All right, save this, run our code. Now we can say print rat 1/3, and we get something that looks more like a rational number. All right, so once we have this data abstraction, or this interface, in place, we're ready to actually implement all the arithmetic operations that we set out to construct in the first place. So for all of these, they'll look pretty similar. Let's just define one of them here. Define add rational. That's going to take in two rational numbers, so we'll call them R1 and R2. Okay. And then the addition operation is specified here, where we have numerator, denominator, divided by denominator, denominator. So we can actually translate most of this pretty straightforward. So we're going to make a new rational out of the results of combining these parts. So we'll say make rat out of, so the top part here, which is numerator 1, denominator 2. So we'll say numerator of R1 plus the denominator R2. And those two things get added together. I'm sorry, those two things get multiplied. I get a similar combination, says numerator R2 plus times denominator R1, and then all that stuff gets added together to give us the new numerator of our result here. So it did essentially this, and then the bottom side of that, the bottom part of the rational number here, would be the product of denominator R1 and denominator R2. So, pretty straightforward. Constructing this add rationals takes in two rational number objects, whatever those happen to be, and using only the interface, so numerator, denominator, and make rational, we construct a new rational number that represents the addition of the input two rational numbers. So let's test this out. Let's run and say print rat, add rat, and we'll say 1/3 plus 1/3. And we get 6/9, which you can imagine is also 2/3. So seems to be working out. So the key concept here, and it's a key concept of data abstraction outside of this example, is that procedures should use the data without making assumptions about how it's maintained. So notice in this add rational example, and indeed if we go through the code for all the other ones here, we're only ever interacting with the underlying implementation via that interface. We're only ever saying numerator, denominator, make rational. There's no mention of pairs anywhere inside this add rational function. It assumes that the interface constructing and accessing the different numerators, the different rational numbers, is the entire interface for that data. It doesn't assume anything about how that data is maintained underneath that abstraction. Okay. So we can do all of that. Now, one of the issues here is that in our output, we shouldn't have 6/9. If we're dealing with rational numbers, 6/9 would be reduced to lowest term, so we'd have 2/3, which would be more of an obvious solution to 1/3 plus 1/3. So what we need to do is simplify our abstraction here. As I say, we need to simplify the rational number inside our abstraction, sorry. So our current form doesn't actually do that, so what we need to do is change our interface. So our make rat shouldn't just combine these two values, it should also reduce our values to their lowest form. So to do that, we can use the built-in operator GCD, which gives us the greatest common divisor. So we can say let G be the GCD of num and denom. Okay, so G is the greatest common divisor between the two integers in our new rational. So if it's 6 and 9, we'll get a greatest common divisor of 3, and then we can divide our values by 3 when we store them. So we can say, instead of just consing num and denom, we will cons, the brackets right? Yep, okay. We will cons num divided by G, our greatest common divisor, and denom divided by G. Close all our brackets and save our code. Now, if we run this using the exact same stuff we've done before, so run our code here, without changing any of the add rat or print rat or anything else other than just how we're combining these things, we can actually use the exact same command, so add 1/3 to 1/3 and print it, and we get 2/3 as our answer. So notice we didn't have to change anything about how add rational works. It's still interacting through numerator and denominator and make rational. The underlying implementation now takes care of lowering our values to lowest terms. So because we have an abstraction barrier in place there, the implementation of our values is separate from their usage, and the usage doesn't need to change if that implementation changes, so long as that interface remains the same. So this interface creates what's known as an abstraction barrier. An abstraction barrier essentially is just a sequence or a group of functions that can separate lower levels of our program from the higher levels. So it can separate what can be done from how it's done, if you want to think of it that way. So for example, from our code here, we have rational numbers in the problem domain. Those are only going to interact with rational numbers through the arithmetic operations. But those arithmetic operations only ever treat rational numbers using the makerat numerator and denominator functions. Now, underneath the makerat numerator denominator functions, this abstraction barrier here, we have rational numbers as pairs, but above that abstraction barrier, we never mention pairs again. And similarly, we can say there's an abstraction barrier just in the pairs themselves, right? We use cons, car, and CDR, but we don't necessarily need to know how those are actually implemented in the underlying language. We can construct rational numbers out of them, and indeed all of these other levels on top of that. So once we have a relatively robust abstraction barrier, or a set of procedures that creates an interface, it can separate how we can operate with these, what we can do with this data from how that data does what it does, how it's actually implemented. And indeed, we can actually take this one step further. So right now, we're implementing rational numbers as pair objects, which essentially makes sense. We have two integers. We need to hold them together, and pairs essentially do that. But a more dramatic example, we could actually store rational numbers using only procedures. So recall the representational condition of a rational number. It's in the notes here somewhere, way back up here. Essentially this, that if we say make rational AB, then we should be able to say, if we call the result of make rational AB x, then we should be able to say the numerator of x divided by the denominator of x is equal to a divided by b, our original values. Okay. Now, any set of procedures that satisfies this condition can implement that abstraction barrier. So if we have a different set of procedures that maybe doesn't use pairs underneath, it can still specify a valid abstraction for rational numbers that we could still use in all of these other values or all of these other operations like addrat and subtrat and all those. So let's see that. Let's create closures that essentially store rational numbers for us. So I'm going to come up here. I'm going to effectively comment out all of these. Oh, VS Code. Use a different hotkey. There we go. So that all works, but let's comment it out so we can make new ones. We'll say define makerat, again with two values. We'll call them num and denom, or n and d. And now instead of storing these things as a pair, we're going to create a lambda. But first, let's keep it in lowest terms. So still let g be GCD of the numerator and the denominator. So we get our lowest term here. And now instead of storing a pair, we'll create a lambda here. Lambda x that says if x is equal to, let's say, 0, can actually be anything, then we'll return n divided by g, so the numerator divided by the greatest common divisor. Otherwise, we'll return the denominator divided by the greatest common divisor. Okay, so it's a bit strange, but if we take a look at this, we said make rat 1, 3 again, so n is 1 and d is 3. It's going to find the common divisor, or maybe we can say 6 and 9, since we saw that example. It'll find the greatest common divisor is 3, so if n is 6 and g is 3, then it will return a lambda that waits for another value x, and using that value determines should I return the numerator divided by g, so 6 divided by 3, or should I return the denominator divided by g, so 9 divided by 3 in our example. So that's great and all. That won't work with our existing numerator and denominator functions, though, because the thing coming out of makerat is no longer a pair. So the thing going into numerator and denominator can't be assumed to be a pair. Car and CDR will not work on a lambda. So what we need to do is define new numerator, call it rat, R for short, and a new denominator. So define denominator of R. So what can go into these functions? So at this point, we're inside the abstraction barrier, so to speak. So we're allowed to look at these things in their implementation view. So if R is just a lambda, what we want to do is use that lambda in such a way that we get this value back, which is to say we need to provide a value to that lambda such that this is true so that we get this as the result. So if r is our lambda, we'd say r as a function, and then pass in a value for x that gives us this here. So to make that true, we just say x equals 0, so we'd say r of 0. Okay, now it's a bit strange. Now if we do the same thing for denominator, we'd say use this rational number as though it's a function, and give a value for x that will make this false, so that's literally anything else, so I'll say r of 1. Okay, now coming down to this other steps here, we say make rat 1/3. So this line here says pass 1 into n, 3 into d, and return a lambda where those bindings exist. So we have the free variables n and d bound to 1 and 3, and that procedure object, or that closure, gets returned. So the thing we store in 1/3 is in fact a closure, a pair of pointers where one part points to the lambda and the other part points to the enclosing environment, in this case where n and d are bound to the values 1 and 3. Then when we ask the numerator of 1/3, we take that lambda, we pass it in as r. Okay, so 1/3 here is a function, specifically this lambda, that gets the argument 0. So if we put a 0 in x, we have this body here where x is equal to 0, so this is true. So we operate this part, and again, because we're in a context where n equals 1, we're going to say 1 divided by, in this case the GCD will just be 1, because there's no other greater common divisor between 1 and 3, so it'll return the value 1. Similarly with denominator, we pass in this lambda called 1/3, we'll give it the value 1, which will make this x equals 0 false, and it will return the denominator in lowest terms. Okay, there's other alternate forms you could use for this as well. You could have all sorts of different things. You could have it with lowest common divisor already stored rather than doing the division at the point of return. You could do it up here and store n and d in this let, since that also creates its own scope, as the lowest common divisor versions of numerator and denominator. Or you could have a different function that uses an entirely different representation. Now the point being, if I run our code here and say print rat, add rat 1/3, 1/3, and enter, everything else still works fine. The only thing we changed in this case was the implementation of our abstraction barrier, but we upheld the same behavioral conditions of that abstraction barrier. Specifically that if we construct something using make rational, we should be able to access the two parts of that, and those two parts divided by each other should give us the same division, or the same answer as if we just divided the original inputs. So abstraction barriers separate parts of our code into logical groups, or logical layers, if you will, where stuff below that layer is more the implementation details, and the stuff above that layer is more the operational details, the things that we want to actually do with those. And so long as we only ever access that information via that interface, then we can change that interface without disrupting all of the code above that abstraction barrier. This simplifies our design. It says, if I want to worry about arithmetic, I only have to worry about arithmetic. I don't have to worry about the underlying implementation of the data that goes into that arithmetic, for example. All right, so we've blurred the line between procedures and complex data a little bit more. So what is meant by complex data or data abstraction? Well, complex data is some collection of procedures on simpler data, so constructors and selectors, together with the specified conditions that these procedures must fulfill in order to be a valid representation. So in general, data abstraction requires that we first identify what objects we want at that higher level, so in this case, rational numbers, for example. Then identify the set of operations for those objects, so the interface that we'll use, that would be our make rational, numerator and denominator, and then only use those operations when interacting with those objects. This will make our programs easier to read, design, debug, and ultimately to maintain as well. That's it for this video. In the next video, we'll go on to use this data abstraction notion and pairs to construct lists.